Exercise 6.23. Let X be a connected topological space and A a subset of X. Prove that if the interior of A and the interior of its complement are both non-empty, then the boundary of A is a cut set, and that pair of sets form a separation of the complement of the boundary. All right, so we're sort of taking a subset and throwing away the boundary and getting at least two pieces, right? At least an inside and an outside, and thereby obtaining a disconnected set. So let's assume that for the subset A of X, both the interior of A and the interior of X minus A are non-empty. Okay, and then in order to prove that the boundary of A is a cut set, we must show that its complement is disconnected in X. And we accomplish this as suggested in the problem by showing that the interior of A and the interior of X minus A form a separation of the complement of the boundary of A. Okay, so what does it mean to be separation? Well, you have to be non-empty, which we already know these sets are. You also have to be disjoint, and your union has to be the whole space. In this case, the whole complement of the boundary. Okay, so let's show that these two interiors are disjoint. And the thing to notice is that while the interior of A is a subset of A, and similarly the interior of complement of A is a subset of complement of A. And okay, but A and the complement of A are certainly disjoint, and so these subsets of them are disjoint too. So we see that the interior of A and interior of X minus A are disjoint. Okay, and then the last thing on our list remains to show that their union is X minus boundary of A. And okay, well, for that, I'm going to use all three of these results up here, these theorems, to do some set manipulations. And so let me just quote them here by theorem 2.6, parts 1 and 2, and by De Morgan's law, and by theorem 2.15, part 2, we have, okay, well, I want to show the union of these two sets is X minus the boundary. So, all right, what is the first theorem give us? Well, that's the one that says that the interior of the complement of A is the complement of the closure, and vice versa. And if I take the complement of both sides here in part 2, then I get that the interior of A is X minus closure of X minus A. So let's replace interior of A right here by what I just said, X minus the closure of X minus A. And then the interior of X minus A is just X minus closure of A. Okay, I'm going to need some parentheses here. Around the two sets I'm taking the union of. Good. Now what do we do with that? Well, De Morgan's law is up next, and it says that the oh, that's a That's a typo right there. I have the union of two complements, and that's going to be the complement of the intersection. Okay. So this becomes complement of the intersection of the two closures. Closure of A. Good. And finally, by theorem 2.15 part 2, the intersection of the closure of A and the closure of its complement is exactly the boundary of A. Okay. So this is just what we wanted, complement of the boundary of A. And we're done. We've shown that these two interiors form a separation of X minus the boundary of A.